Hi everyone. We are now going to construct 1 minus alpha confidence intervals, CIs, for P, a population proportion or probability. For example, little p could be the probability that a coin, like a magician's coin, comes up heads. Basically, the probability of heads for the coin, the true probability of heads based on physics. Here, I'm going to discuss the anatomy of these formulas for these confidence intervals, and this anatomy should be somewhat familiar from lessons 28 and 29, when we were estimating mu and doing confidence intervals for mu, a population mean. And then later on, I'll discuss the theory behind this, and if you don't understand the theory, don't freak out about that. If you understand the examples later on, that should be sufficient, but try to get as much of the theory as you can so you can get a feel for why these things look the way they do. But again, don't freak out about the theory. But first off, let's look at the general anatomy for these things, and this should be familiar. A 1 minus alpha confidence interval, CI, for P, is given by this, and this looks very natural. Because this here is saying that our confidence interval for P is going to be centered at our point estimate, the sample success probability, P hat. Just as when we had a confidence interval for mu, the confidence interval was always centered at x bar, the sample mean. So once again, like for a population mean, for P, a population proportion or probability, the center of any confidence interval will be at P hat, the point estimate, the sample proportion or probability of success. So that part makes sense. Also, E is the half width of this interval. So the margin of error is from here to here, and also from here to here. The limits of the confidence interval are obtained by taking P hat and then adding and then subtracting this margin of error, E. So from P hat, you add E to get the upper limit of the confidence interval, and then you take P hat and subtract E to get the lower limit of the confidence interval, just like before. Before, when we did confidence intervals for mu, we would add E to get the upper limit and subtract E to get the lower limit. So far, this should be very familiar from what we saw in lessons 28 and 29, except that now we're doing a confidence interval for P, not mu. And in fact, if you look at the anatomy of this margin of error, even this part is familiar, right? That's a critical value. It's the positive critical value for the z distribution, given the confidence level of interest. So again, for a 95% confidence interval, this will be 1.96, just like back in lesson 28. So you might even remember some of these. For a 95% confidence interval, 0.95, this will be 1.96, the same as for lesson 28. But now this part here is not so familiar. Okay, before in lesson 28, we used the standard error of the mean, right? In lesson 29, we used an estimate for that. Well, here, this here represents a measure of spread as well. This radical here, the square root of P hat Q hat over N, this estimates the standard deviation for the distribution for P hat, the sample proportion, as a random variable. Now, if that seems confusing, I don't blame you. I'm going to discuss the theory behind that next. And even then, get what you can. If you understand the examples later on, you should be fine. Again, we're trying to get as much theory as we can here. But again, overall, the structure of this confidence interval is very similar to what we saw before when we did confidence intervals for mu. We center the confidence interval at the point estimate, in this case, P hat. And then we add and subtract a margin of error to get the limits of the confidence interval. And the margin of error is obtained by getting a critical value, a z-score in this case, times some measure of spread for the distribution of interest. We'll talk more about that in just a minute. All right, again, these formulas make sense because the confidence interval the CI for P, is symmetric about the point estimate, P hat. The margin of error is the product of Z sub half alpha, the positive critical value from the Z distribution, which depends on the confidence level. So the larger the confidence level, the bigger this thing is, and the bigger the margin of error. And then this thing here, the most confusing part, this thing here, which again estimates the P hat distribution. So here's the part where, okay, get what you can. Okay, but don't freak out. So why does this estimate the standard deviation for the P hat distribution? All right, well, what is P hat? What's going on here? All right, remember, X is the number of successes. In our coin example, X is the number of heads that we're going to get. X is the number of heads we are going to get when we flip the coin. N times, where N is pre-specified. You could think of N as a sample size. But here's the thing. Before we flip the coin, X is a random variable. We don't know its value yet. X is a random variable. We don't know its value yet. But we do know its distribution. X will have this distribution. X will have a distribution, a probability distribution, approximated by the following. X has a probability distribution. It was really a binomial distribution. Okay, it was really a binomial distribution, but we're going to approximate under the conditions before. If NP hat and NQ hat are both at least 5 up here, if NP hat and NQ hat are both at least 5 up here, under those conditions, okay, we're going to approximate this binomial distribution with this normal distribution. Remember, NP was the mean for the binomial distribution, so we're going to take that as the mean for the approximating normal distribution. And root NPQ was the standard deviation of the old binomial distribution. We're going to take that as the standard deviation for our normal distribution. But now wait, in the end, we're not so interested in the number of heads. We're interested in the proportion of heads. We're more interested in P hat as a random variable. P hat is the sample proportion of successes as a random variable, okay? And how do we get this sample proportion? We get X, the number of heads. We get X, which is the number of heads, and we divide that by little n, the sample size or the number of trials. Again, this can be thought of as a sample size. So for example, if we eventually end up with 60 heads on 100 flips, then P hat will end up being 0.6 or 60%. But again, P hat is a random variable before we flip the coin. P hat is given by X over N. It'll be the number of heads we get over the number of flips, the number of trials. So it will have approximately this distribution. And it does work out cleanly. The mean is going to be NP divided by N, which ends up being P, the true probability of heads. The standard deviation for X was root NPQ. It turns out we divide that by N to get the new standard deviation of root PQ over N. But wait, when we construct our confidence interval, we don't know the values of P and Q yet. So we approximate them by P hat and Q hat. And that's why we get this radical here. I'm trying to explain why the radical looks the way it does. If you didn't get that, don't freak out. But try to get whatever theory you can from that. We're going to apply this in examples later on. And again, if you get the examples, you should be fine. Don't freak out so much about the theory here.